F is 6,000 newtons. E is what we're trying to figure out. We want to know what the field strength is at that particular point. And Q is the electron. So that's the charge on an electron, which is 1.6 times 10 to the negative 19 coulombs. Negative 1.6. It's the size of the charge that really matters there. So 6,000 divided by 1.6 times 10 to the negative 19. 3.75 times 10 to the 22. Seems reasonable. Yes, Sarah?
Okay, I use the negative because that's what you gave us. Does the sign on the number that you get matter? Like, would it matter if you got a negative?
It wouldn't really matter, no. I would accept both answers. The negative really just tells us it's going to move away from the... Yeah. But we want to know what a positive test charge is going to do, right? So this is just telling us the magnitude.
We want to know what the electron.
Oh, the electron. No, we want to know what is the field strength. And we always talk about field strength in terms of a positive test charge. I won't mark you wrong either way. It's fine. But
even though it says that you have an electron, when it says the word field strength, it just means
no. The field strength is just when we're talking about the field itself. It doesn't matter that it's an electron that we've placed there. The electron is our test charge. So we always describe field strength in terms of a positive test charge. Again, I'm pretty easygoing. I don't care if you leave the negative there for your calculations. I just want you to realize that we're talking about a magnitude. We're talking about how strong that field is at that point. And usually you would report it as a positive. Okay? Adriana?
So what is the charge of the electron ever change?
No, that's a constant. 1.6 times 10 to the negative 19 coulombs is a constant. So it's always, and I will give that to you. I'm not going to make you memorize that. I'll give you that, and if you need the masses of a proton and an electron, I'll give you those as well. Maybe in grade 12 you might have to memorize them, but grade 11, I'll help you out. If you placed a proton at this point, how would its acceleration compare to that of the electron? Opposite direction, good. It would have a slower rate of acceleration because the mass is significantly greater. So it... Sorry? No, its initial rate of acceleration would be slower.
I'm just thinking, if you're like trying to pull a plane, it's super hard, but if you're trying to pull like a motor, it's really fast.
And an electron, a proton weighs 1,800 and something times that of an electron. So the plane marble analogy actually isn't that bad. As far, well, maybe the off, right? But yeah, it's the same amount of force because it's got the same charge. And we did a practice question like this. Because it has the same charge, it has the same amount of force acting on it, but because their masses are different, their accelerations will be different. And if you substitute into those formulas, Helen, you'll see that increasing the mass. Oh, okay. Increasing the mass, it's just F equals ma. So you've got F equals ma. So you have the same amount of force acting on the proton and the electron because they have the same charge.
Same acceleration, different.
The masses are very different. So if you increase the mass, decrease the acceleration. So proton weighs more, therefore it will accelerate at a slower rate. Okay? If you were able to increase the charge on the electron, so instead of it being 1.6 times 10 to the negative 19, if we were able to change that constant somehow, what would happen to the acceleration of the electron as a result? It would increase because you have F equals E times Q. If you increase Q but keep E the same, I gave away another answer, then the force acting on that electron would increase. So if the force increases, therefore, the rate of acceleration would increase.
Wait, so it would repel faster?
Yeah.
Oh, you get it.
Okay. What would happen to the field strength? It would stay the same, and I just said that. So the field is not affected by the test charge, unless it's a really, really big test charge. And to the force on the electron, it would increase as well. Again, I gave that away. Helen?
Sorry, so the answer for number 2 was what? Would it do the same thing in a positive fraction?
For number 2, the proton,
Yeah,
it would do it in the opposite direction.
positive 3.75 times 10 to the 7 negative 22 coulombs for Newton's proton.
No, that's the field strength. The field doesn't.
It would do the same thing in a positive fraction.
No, it wouldn't do the same thing. It would go in the opposite direction, and its rate of acceleration would be slower. Okay. I think you missed that class, so take a minute and talk to me at the end of class, and I can show you the math behind that. Okay? Because we did go over it in class. So, yeah. Below are oppositely charged plates. Draw the field that results. So in the middle here, what are my field lines going to look like?
Going down
Going down? Why do we draw them going down, Helen?
because of what a positive would do.
Yeah, what would a positive do? A positive is going to be repelled. Now out here is where it gets a little tricky. It kind of goes there, curves back, then goes there, curves back. And then I'm not going to get too fussy about out here.
Would they just go down? Yeah. Okay.
A positive is going to be attracted here, right? And out here it's going to be repelled. Now, if you've drawn something similar to that, maybe you have less lines, maybe you have more lines, but similar, then that's okay. If you were getting really, really serious, you know, you could put an extra one like that going like there, but I don't care. Oops, I want that to happen. All right, so an electron is placed at point P. Describe its motion. So what's an electron going to do?
Towards the positive.
It's going to move towards the positive plate. Can we be a little more descriptive or specific? It's going to accelerate towards the positive plate. It is repelled by this negative plate here. It's repelled by that one. It's attracted to the positive plate there. So it will accelerate. Whenever you see describe its motion, try and be as specific as possible. Usually they're looking for more than just it's going to go that way. Talk about its rate of acceleration if it has one, or if it doesn't. If it has constant velocity, talk about that. Talk about how it's changing its velocity or changing in direction. But be as specific as you possibly can be. How does the motion of a proton differ? Well, we just talked about this in the last example. It'll accelerate towards the negative plates. Compared to the electron, it would be opposite direction and a slower rate of acceleration, right? So it's the exact same as the last problem. You put a proton there, it has a different mass, it's going to accelerate. And like I said, this is like favorite evil exam question. Proton and electron. If you placed an electron at point R, right over here, which is the same distance from the negative plate as point P, how would the motion of that electron compare to that to the one from question 1? Sarah?
It would repel with negative plate at a faster acceleration.
So you're saying it would repel away from the plates at a faster rate?
Yes.
Yeah? Who agrees with that one? Anyone disagree?
No, it did same rate. Sorry.
Same rate?
Yeah. But
Well, our options are it will repel from this plate. That much is given because it's a negative plate, negative test charge. It's going to repel. Our options are slower rate, faster rate, or the same rate.
I still change it again.
You want to change it again?
yeah,
Slower rate. Okay, why do you think it's slower rate?
because in the original one, it has both the repulsion and the negative and the attraction. direction positive, then he's going to be canceling.
Right. For point P, for those of you that missed that, at point P, the electron it's being repelled by this charged plate, and it's being attracted by this positive plate. So there's two forces acting on it. Here, it's only being repelled by the negative plate. And because it's the same distance from the negatively charged plate as P, it's going to it should have from P the same amount of from this negative plate the same amount of force. But for P, there's the extra force from the positive plate. So the field should be stronger here. Okay? So it should, this one would accelerate at a slower rate. An object placed at R has a force of 50,000 newtons. Field strength at this point is that. What's the size of the charge of the object? 8? Okay. 50,000 newtons. This is F equals EQ. So 50,000 newtons is equal to 5.78 times 10 to the 12 newtons per coulomb times Q. So 50,000 divided by that big number, 5.65 times 10 to the negative 9.
Yep.
Sounds reasonable. Anyone very much disagree? No? Oh yeah, sorry. Oh, I forgot my units.
I got something different.
You got something different?
I got 8.6.
7.75. 65.
8.6. I got 8.6 times 10 to the negative 9.
Oh yeah.
Oh, that's not a subset.
So 8.65.
65.
Yeah, 'cause if you're dividing 5 by 5.78, it should be times 10 to the negative 9 still?
Yep.